All right. So are you all familiar with that? Those procedures you're supposed to use to come on campus? I'm going to just show them to you. I mean, they want people to use that pre-screening out. So, I mean, I'm willing to just push those word on you, know, if you're not sick or anything. I mean, you don't know if you got the thing, if you got it, I don't think, but just anyway, that's what we're supposed to do. But I don't exactly see a whole lot of cleaning supplies except for that back there. So, probably when you leave, wipe down your seat, the desk and seat. All right. So, this is also a little concerned about measures of variation, because remember, the standard deviation, as I had said, is the most important measure of variance, okay, of variation. Because what the standard deviation does, it tells us how many standard deviations we are from the mean. So remember, for symmetric data, we've got this mean right in the center, and that would also be the median if we've got symmetric data. And each one of these hops is one standard deviation. It goes both on the left and on the right. So there are really 6 standard deviations for the most part underneath that curve. There's a little bit more on either side, a very, very small amount, because if you understand anything about asymptotes, that area gets smaller and smaller as that line goes down. But for all intents and purposes, almost all that data can be encompassed with 3 standard deviations on either side of the mean. One standard deviation is 68%, 34 here, and then 95%, which is going to be important. That 95% keeps popping up throughout the course, as we're going to see. 95% is the lion's share of the data. You can still have almost all of it, but we're going to see that there's some tests that we can do to deal with 95% level of confidence. So 2 standard deviations gives us 95%. Okay, so that's what we call the empirical rule. It's more or less accurate, because if we take any whole number of standard deviations, 1, 2, or 3, we can pretty easy at a glance tell how much data we're dealing with. All right, half of it's over here, and half of it's over here. Negative standard deviations, positive standard deviations. So if we want to find out how many standard deviations something is from the mean, remember this data we looked at last time, I believe it was. This was the number of age 65 and older for each state in the District of Columbia. So we got 51 pieces of data, and all these are stem and leaf, because that was a pretty good information to use with stem and leaf, because it's only got, I believe, the lowest is 8 and the largest is 17, I believe, or 18. So you only have a handful of stems, and then it was real good for doing that stem and leaf. Now, what they're going to show us with this is they're using the calculator to do this. They ran the, what we call the descriptive statistics. That's where you put in one column of data, and then you select bar sat underneath the math button. Let's see. Since I don't have that on here, I want to see if I can put that on here so I can show you. So this is the one that I've. And this only works for Windows. So if you got a Mac, you got to find something else. But this is a great little tool, so you don't have to go out and buy, you know, a $100 calculator, because I hate to see people do that for just one semester. All right, so. So once you do this the first time, you got to show it where that second file is. And I'll put them all in the downloads. This is what I did. Oh, I got to put all. And where's it? Yeah, there it is, the bin file. And then that's the guts, because you can get several different types of calculators with it. So as I had said, if you go to math, oh, wait a minute a second, stat, this is where you put in your data. So if you want to just put in data there. If you got the actual physical one, then it should work more or less the same way. Oh, watch, I'll put it back in there. Okay. So go back over to stat, and then you click enter immediately. You don't have to exclude anything. And that allows you to edit. That's why we're just putting in that little array, that little data set. See? I just put in 5 values. Now, to actually run the calculations, same button, stat, except you're going to click over with the little right button once, and then you just hit. And by default, and there it gives you all those things. So that's where all that's coming from. It gives you everything that we've looked at so far. The mean is the same, whether it's the population or the sample. These two, I don't know what the role we need those for. Here's the sample standard deviation and the population standard deviation, because it doesn't know which one you're using. If you've got a sample, so it does both. Okay, and then we'll see in the second, or the rest of this chapter, there's some more things that we're going to look at there. We're not got there yet, but this is what they call the 5-member summary. We'll look at that a little bit later. All right, so that's where this comes from. What they've done is they've ran a histogram for that. Now, I don't know if they did the histogram with the calculator. They may have. But that's the histogram for it. You can see that it's more or less normally distributed. You have to sometimes have a good imagination, because very, very few data sets in real life are going to be perfectly symmetric. You know, optimally, you want one that increases at the same rate, gets a peak, and then you come back down at the same rate where it almost looks like a mirror image. But that's very rarely going to happen in real life, so you got to have a good imagination. And as far as this text is concerned, that's considered approximately bell-shaped. But they gave us these 2 values here. That was the mean and the standard deviation, okay? Those are the ones we're really concerned about once we find out that it's normally distributed. Have y'all been in any other classes face-to-face? Strange getting used to all this.
Yeah.
I mean, I've not been in a regular classroom since March of. Been online.
Coming here, nobody's here.
Yeah, I mean, they can only put 10 people in there.
Are you also not around? Because I'm not. I live like across in the sticks, and I'm over here. Yeah, that's like the big part of me.
Oh, were you coming like from Lafitte or something, or
From
go close? Oh, right. Yeah.
Like I moved down here, so like I moved down here this Sunday.
Oh, okay.
Wow. Yeah,
Yeah, we used to get, when we used to have a Covington, dug out, but we used to get a lot of people coming from up there.
Well, they used to have one this side.
Yeah, I know, it's like, I know, I was the, one that ran both of those, and then that youth school wanted that area, so. But anyway. Hmm? I don't know. Where do you see those at?
That's what I'm asking.
Well, that was that thing I showed you here. This is the classroom rules.
Oh, yeah, from earlier.
I mean, so we have, you know, there's no light, it looks like there's paper towels and we have spray. And technically, you're supposed to go through that app, but I don't even know how to get this kind of place. I mean, I'm not gonna push that unless I really want to. How do you get around it? Well, it's just some kind of app, they've been putting it in the email for 6 months. And some buildings, you'll go into some buildings and they'll make you take out your app before they let you in. But I forgot what the name of it is. Huh? Yeah, I'm gonna say that, that's a bunch of stuff. All right, so, let's go back to this. All right, so remember, the mean was 13.249, and the standard deviation is 1.6827. Now, I said is, right in the middle on this thing, that's the mean, okay? Now, the standard deviation, this value right there, that's what's calculated. So, subtracting one, and then adding one to be one standard deviation from the mean. So about 68% of the data lies between 11.57 and 14.93. So that's the boundary for 68% of the data. Minus one standard deviation plus one standard deviation. And that was your mean. All right. So, to get 95%, well, you do two standard deviations. Just multiply that standard deviation by 2. It's 3.3654, two standard deviations. Subtract it, it gets you about down to 9.88 on this side. And then adding it, hold on a second. That's supposed to be 13. That's supposed to be 13. There we go. So remember the mean right there. So there's a line in the middle. That's why that's always the same. And two standard deviation was the 3.3654, and two standard deviations and three standard deviations was 5.0481. So then you get almost all the data from here to here is that negative 5.0481, and then the plus and plus in is on that side, and that's how we get those two numbers.
Is there a reason that goes from thousands to 10,000 to hundreds, right?
No, this is rounded off. Because you can't really, it helps you visualize a little bit better if you don't round it off. All right, but you still got to watch what they ask for as far as what decimal place. So this is like that. I rounded it off to, I think that's what they did too, but. Well, then, the general rule is one data, what was the thing? One decimal place beyond what your original data was. That's the general rule. So, if it doesn't say, then just go one decimal place beyond. So, in other words, there was this, thing here. They told us about that, see? Nope, that wasn't it. It was by the mean. See, they went out one. See, the mean is rounded to one more decimal place than the original data, and that's the same thing with standard deviation. But like I said, if they ask you for a certain decimal place, then you would go out to whatever they wanted to. But generally, good practice, one decimal place beyond. See, so these were all whole numbers. So we went out to 1/10. All right. So this is to show the empirical rule. The empirical rule is we have that approximately bell-shaped data, but not all data is like that. So there's another rule, but it's pretty much the same thing. It's called Chevychev, and it's called an inequality because they're not going to say approximately how much data. What they said will say is at least a certain amount of data. So if your data set is not normally distributed, which could mean it could look like anything. It doesn't have to look like this. But it's all over the place, and this is certainly not normally distributed data. So that's why the only thing we can use here is Chevychev's rule. And Chevychev's rule is just going to be less exact. I mean, this formula is not really necessary, but this is how these two things are derived. If you take 2 and put it in for k there, that's 1 over 2 squared, or 1 over 4. 1 minus 1/4 is 3/4. And then for here, it's the same thing. If you put, let's see, hold on. And 3 in there for, this is 2 standard deviations and 3 standard deviations. There's not 1 for 1 here. It's only for 2 and 3 standard deviations. So with 3 standard deviations, 1 over 3 squared is 1/9. 1/9 from 1 is 8/9. So this is, well, the only thing I may tell you about this is just that it's an at least thing. When you see the word at least, it means that you're going to these values of 75% and 89%. That's the key word, at least. 75 and 89%. And, you know, there's formulas that you get to make use of here. Like if you come over here, you don't have to worry about memorizing anything. And they actually put these into the test somehow as well. But you see, like on this formula sheet, so you don't have to remember, you know, some of these things I'm telling you. But this formula sheet is still the official one for a face-to-face class. But I suspect we'll be doing the tests online for this semester. But anyway, like you got your empirical rule. And if you can't remember 75 and 89, then you can just stuff 2 or 3 in there, and it'll get you back to 75 and 89. All right, so there's this thing called coefficient of variation. I don't know that it's really all that important, but they may ask you a couple of questions in homework. I don't even know that. It's one of those things that makes it, doesn't really make the cut in chapter 3 because it's not that important, but I guarantee you probably have one more question or 2 about it. But coefficient of variation is just the standard deviation divided by the mean. And what that does is like for example, we got two different situations here. And the coefficient variation for precipitation and for temperature. So, they gave us the standard deviation and the mean for precipitation and also for temperature. So then we can calculate those, and the larger that value is, the more variance there is in the data set. All right, so here's the big, this is the kind of the important stuff, measures of position. And the calculator, as I had said, is for any data set, you get all of these things for free with this calculator. See, as I said, there's the mean, the two that you don't really need. You take those out of there, the standard deviation for the sample, or the population, and then these are those measures of position we're going to be looking at here. This tells you the minimum value, the maximum value. It gives you the median, and then it tells you something called quartile 1 and quartile 3. We'll get into a little bit detail on what that is.
After you have to do that and bring it to that column, what button do you press to get it to go show you all that?
To show you what?
You go to that.
You go back to stat, and then you hit the right key, the key on the right, the one, the arrow key. Look. So once you put it in, you put it in there. Then when you want to calculate, you click the right one, and there it is. The very first thing you get to. So stat, and then hit the right shift or whatever that is, right arrow, and then just hit enter a few times. So that's the one you want. I'm not sure what that one's for, but that right there is the one that we, you'll be using that quite a bit through the course. All right, the first thing, as far as measures of position, are Z-scores. The Z-scores let me see this here. Let me do that and get that out of the way. So the last day I really have to worry about it. Plus I get to know you all a little better. All right, so Camille. Oh, there's there out there. Somebody was locked down, don't seem like. So Deborah, Amelia, Christina, Justin,
No, we're not going to break up.
Kayla Jenkins. She called me and said she's not coming. Candace and Christian Williams.
Okay.
Okay.
I write CJ though.
CJ, okay, I'll try to remember that.
I'm doing all this, not camera.
All right, so one of the things that these scores is good for is to be able to tell whether somebody measured against their particular group are taller than average as compared to their group. In other words, we know that a 73-inch tall man is taller than a 68-inch woman, but if you measure against their own gender, things are going to change because how many and what the Z-score is the number of standard deviations that is from the mean for that particular data. So if we want to find out who is taller relative to the gender, a man 73 inches or a woman 68 inches tall, well, here's what we do. We got this thing called the Z-score. All right. If you had math 120, you would have got this. They go over the Z-score there. But the Z-score is just simply whatever value you want to measure for, you subtract the mean from it, and then divide by the standard deviation. All right, and these values, for the most part, will be between -3 and +3. They can be smaller or larger than -3, but it's just not very likely, very, very unlikely, because 3 standard deviations from the mean on the other side. So that's almost all of the data. There's not much out there. But generally speaking, they're going to be in that range. So let's do the men's height. 73-inch male. The mean for male adult men was 69.4, and then standard deviation was 3.1. And then if you wanted to make sure that was right, let me just show you. 73 minus 69.4 divided by 3.1, and you should see the same thing. That's 1.16. For the most part, Z-scores are fine if you just go out to two values. A calculator can get it more exact, and we're going to find out in chapter 6 what those are used of, another use for those. Now, the woman's height, and we'll take the word on this, 68, subtract the mean of 63.8, and then divide by 2.8, we have a Z-score of 1.5. And as I said, the Z-score is a standard deviation. So, 1.5 let's see if I can write something to show you. I'm going to have to just draw it up there. I don't want to touch any markers, but and of course, none of the markers are going to work. There we go. So this is a little better. So this is 0. So 1 is here, and 2 is here. Then this would be 1.5, and then this would be 1.16 around in there somewhere. So that's 1.5, and that's 1.16. So what that number of 1.5 tells us, that that's a higher positive number than this one. So this person is taller with respect to their gender. So it's a higher standard deviation. If it had been on, the other side, in other words, these were negative, then we could look at it just the opposite as the, a negative 150 would be further down that way, so that person would be shorter with respect.
If this was like a bar graph, they would have had men's height up next to women's height to get the standard deviation. My question, I don't understand why the standard deviations are different for both of them.
Well, okay, remember, standard deviation is how spread out data is from the mean. So, this is, I'm pretty sure this is what we'll call population parameter, because what this is data that is been calculated over years and years and years of collecting data. And so, the standard deviation, now when you say the standard deviation, you're talking about this value here, and that value. Well, this means that there's less variance in women's heights overall. So,
Makes it higher, which makes the overall number like higher than the man's height. The than these four.
Yeah, and this one's higher, so it means that there's more extremes in the men's data set.
I understood that until you drew that, because now I don't understand why they end up on the same graph here.
Because we're comparing them.
Okay, so that graph that you would make like way after you did all of it.
Yeah, see, these things now are in the same universe now.
Okay.
Once we do a Z-score calculation on here, we can compare any data set with another data set.
So originally there were two separate ones,
Well,
or at least two separate lists of data.
oh yeah, two separate lists of data for sure. Yeah.
Yeah, I think you would put it in a graph.
So that's just, again, the empirical rule, you know, is also falls in this category of measures of position as well, but I guess I could have wrote it on here. Remember, that's the lady type and the man type are right there. All right, so we talked last time about the median. The median is the value in the middle of a data set that's ordered. The data is ordered smallest to largest. Then the median is that value that's in the middle, either the one value in the middle or the two values in the middle that we add up and divide by 2. This is an even number of pieces of data. The quartiles are very similar, because median means that we're taking this thing and putting it in half here and half there. Because the median is the same as the median. The mean is the same as the median for this type of data, normally distributed data. So 50% is over here and 50% is over here. Well, what we can do is go one step farther and have quartiles. In other words, make this one in half. Make this one in half. Oops, well, it's not one in half, but that's probably going to be a good one in there. But the quartiles just means it's in 4 parts, 4 even parts. You know, 1, first, second, third, and fourth. 4 equal parts, 4 quarters. And that's what a quarter is. Quartile means quarter. So the first quartile means you got 25 down here, and then you got 75 up here. If you're at the second quartile, which is also the median, you got 50% and 50%. And then if you go up to the third quartile here, you got 75% down here and 25% up there. All right, so they show us a way to calculate the quartiles, and it's essentially by position. So what we will do is just take the number of pieces of data, which is what N is always in this class, and then to find the first quartile, we multiply by 0.25. And that will tell us what position, well, once we round it up, the quartile is the average of the number of position and number in all plus what position, very similar to the median. So if it's a whole number, you got to find the one in the middle. If it's not a whole number, then you just bump it up to the next one.
In the other one, I was doing like 95%, and then the almost all, it is just understood when you're at like the second quartile and 1550.
Yeah, I mean, that's all this is. It's just
Almost equal.
25.
Almost all, not actually.
See, 25% here. There's 25% in each one of these pieces.
Right.
And you're like going across here. So you get up to this point, you got 25% of the way, 75% to the go.
Right. On the last graph, it said almost all.
Yeah, almost all
Saying that.
would be essentially those two right there, yeah. Almost all is like 99.7%. And that's where the 3 standard deviations come in. At 3 standard deviation, you get almost all of it.
And when you do that, like, okay, then the first section, without that, like, L equals 125 times the number, so that's like when you take the, like, this is how my brain did that, I want to do this right. So it's like when you take the number of different values and you times it by 0.25. So whatever number you get, is that the number, like when they're in order, is that the number?
Yeah, watch.
That doesn't matter.
Look at this. All right. So, here's some data for yearly rate, it's annual rainfall in inches during the month of February over 45 years. Actually, they take several years, but there's 45 value to 15 in each row. So, we can find the median by finding the two in the middle if we wanted to, but let's kind of find the quartile first. So, 45 pieces of data times 0.25 gives us a value of 11.25. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, here, that's where we get the 11.25. So it's somewhere in between these two, is what that's what I'm saying.
Okay, so that is a.
So the way the rules work is, since it's a partial value, 11.25, we just bump it up to 192. Just bump it up to 192. The other directive, and this doesn't happen that much actually, is if it's a whole number, then you got to do the same thing you did with the median, which is take the two in the middle and add them up. If it comes out of a whole number. It doesn't happen very often. All right, so see, this is the first quartile. Now, there's 45 pieces of data, so that means, let's see, how many is going to be on the other side? Because that's an odd number of pieces of data. So that's smack down in the middle. So you got 15, 16, 17, 18, 19, 20, 21, 22. And then there's 22 over here, and there's your one that's in the middle. It's another way of looking at it is like this. But this, I don't know if this mentions it in this book. So 45 plus 1. So the 43rd position is 26. 23. So that's the one right there. That's the 23rd position. So you can handle it that way too. And then the third, it's just a matter of 0.75 times 45, which gives us 33.75. So again, it's not a whole number, so bump it up to 34. And so, let's say 30, 31, 32, 33, 34. Because they're all ordered. 15, 16 through 30, and then 31 through 45. So all ordered, so all we have to do is just count once we figure these out. So now, that's the information right there. If you were to take this data and put it into that TI, and do that same calculation with the stats again, on the second page, you have that information right there. So now, these are the three right there that you just kind of went through. The minimum should be pretty obvious. That was 0, and the maximum was but it calculates it for you, 13.68. So that's what we call the 5-number summary. So the minimum was 0. So this was Q1. The median or Q2, Q3, and the maximum was 13.68. I think you might be looking at them, I forgot what they were.
0.9.
Yeah, 0.92. Uh, 3.12, and then this is 4.94. And see that they're all sequential, well, you know, in order. And then, like I said, that's just called a 5-number summary. And we're going to use that for something interesting in a bit. And it's build a chart, what do they call it? Box and whisker plot. So that's another way to be able to look at data and tell us it's the method. So see, they put it in there, and you get the same stuff back. So this is what I was trying to draw over here. Now this is more realistic to that particular data because the third and the highest piece are a little bit more spread out than the early ones are, but that's the 0.92, what was it, 0.92, 3.14, 4.94, and then that's the 13.68. So they're just kind of showing how it's breaking down. We're going to create something that looks a little bit better looking than that. All right, now percentiles are really, once you got the idea, you know, the idea behind quartiles. Well, a percentile is just a percent. So instead of dealing with quartiles, you're dealing with individual percent. So what you do is you essentially do the same thing, except you multiply times whatever percent as a decimal. In other words, so if you're looking for like the 79th percentile, it's 0.79 times 45. And then whatever that comes out to.
I'm sorry, where are you getting the 45?
Wasn't that how many pieces of data, or did I write it wrong, down wrong?
Oh, okay, I see what you're saying.
So 35, so 36th position, the 36th position, so let's take 30. The 1, 2, 3, 4, 5, 6. So that would be the 79th percentile right there. So percentiles pretty much just work just like the quartiles, except, you know, you're not rounding it off to a whole quarter, or they even have things called quintiles, and they have deciles, but really the most important ones are the quartiles. And because we're all building up something here. But just to show you that percentiles all work the same way. And if you had any other kind of a teal, you know, that was decile, you know, you multiply by to find the third decile, 0.3. You don't have to do that in here because the quartiles are by far the most important thing. But they also show you that percentiles work by the same procedure. Now this was an example of one where they both come out to, it comes out to a whole number. So the 60th percentile, and remember, that's just 0.6. I don't know why that was taken system, they have to put it over 100, but just to show you that that's 0.6 times 45. So the 27th position would be, since it's a whole number, you take the 2. If it had been 27.1, then you would use that. But since it's the 27th position, you use the 2 right next to one another, add them up, and divide by 2. Because that was the same instruction they gave in the quartiles, but they just didn't show you one until now. All right, so this is what we'll concentrate on. All right, so let's figure out these 5 number summaries and then how we can use them to help us with data. All right, so you remember we figured these out? So this is a 5 number summary and the root of this. All right, so what can we do with that? All right, well, first thing, let's talk about an outlier. An outlier is a value that's considerably larger or smaller than most other pieces of data. We look at that example with income, like people living in an apartment complex. You had somebody that had $1 million windfall, and their income, yearly income, went from $25,000 to $1,025,000. And that outlier caused skewness for the mean, because that's the nature of the mean. It's sensitive to outliers, that values that are very low, very high. If you've ever done test grades and you had 3 good test grades and 1 bad test grade, that real low test grade pulls you down. That's called skewness. It's an outlier in a sense. It could be the correct value, but it's just that the outlier is an extremely high or low value. So we keep track of them.
So that's like in the last set of data, you have pointed out that the height was like close to the outlier.
Which one?
It was when we first started.
Was it this?
It was the one about the old people.
Oh, yeah. That's a good one because it's also a good exercise. Here, where is it going? There it is. Yeah. And remember, 95% is between, what did we say it was? So 95% is within 9.8, yeah, that's the 95, and 16.61. So let's go and just look. I think there's 3 values. There's 1 lower.
And this is 8.1.
Yeah, 2 lower, and there's 1 higher.
And this is 17.8.
Yeah, so there's 3 of them that are outside of 95%. So let's just look at that in a second, because this, I think, give you a little insight. So there's 51 pieces of data, so 51 minus 3 is 49, right? So 49 divided by 51, so that's 96%, so pretty close to 95. It'll never, as I said, it's really going to be exact, but 96%. Because that number, or within, because this one was out, that one was out, and the 13.8. And then I think almost all gets even better, because it's 18.2 and 18.31. There was nothing greater than 18.31, I don't believe. And the only one that was lower than 8.2 was Utah, 8.0, 8.1. And then if you calculate that, well, that's 50 over 51. So 98%, so getting close to almost all. So it's done, the rule actually does work. I mean, it's not exact, that's why they say about or approximately. All right, okay. So this is what I wanted to look at. All right, so I just wanted to show you that that was a 5-number summary, the same one there. Let's look at this last one. Outliers is considerably large or small value. All right, so these are supposed to be temperatures taken during summer days on 8 days. And you'll notice that most of them are 80 something or 90. And then when they have a problem, is 8.45. Now that right there would be considered an outlier, and it's most probably a mistake because unless, you know, some kind of weird weather, some conditions in the summer, somebody just typed in the decimal place wrong. And so what could easily be done in real life is go and check it and correct it. So it's considered an outlier, and that allows us to know what to key in on and just see if it's right. Because it is possible that an outlier is actually a viable value. They said this is, if it's possible, you fix it. If not, then we'll see what to do with it. All right, well, first thing we got to have is what's called the interquartile range. Remember, this is Q1 and Q3. So what we do is we take this value and subtract Q1 from it, and that's what's called the IQR, interquartile range. All right? Now, what we do is, and this is kind of a theoretical thing, we'll see how to do it in a second. We take that interquartile range and multiply it times 1.5, subtract it from Q1 and add it to Q1, and what that does is give us these outlier boundaries. Look. All right. This was some data for days in January and the number of absences in middle school in Montana. And they went ahead and popped it all in the calculator, and they got the four, you know, the 5-number summary back. So Q1 was 45, Q3 was 59. So IQR is a high of 59, take away the 45. So the interquartile range is 14. So from here to here, it's 14 units. All right. Now, multiply that by 1.5. We don't show you, but 1.5 times 14, I think that's 21, right? Let me make sure. All right. 14 times 1. Yeah, so 21. So what we're going to do is we're going to subtract 21 from 45. So that's 24. That's where we get that at. And then Q3 plus that same value. So that's 80. All right, now these are what are called lower and upper outlier boundaries, and that's where we're going to look and see if there are any issues with this data. All right, are these outliers? Well, 100. Yeah, there's a value of 100 in there, and that doesn't mean that it's necessarily wrong, but we got to look at it. And what I would say is, I don't see how it could have been a mistake, because maybe it could have been 10, but even that would be an outlier in the other direction. So what I would just probably say is this looks like a fine value, but we're gonna mark it as an outlier just because it is high. Because, that's 100 days, and 100 people out, and, most of the other ones are right there in the 40s, 50s, maybe in the 70s. What?
I don't know, in Montana in January, it's probably better.
Well, it may well be, yeah, that's a good point. I didn't think about that. I thought maybe it was a sick day or something. That's what I was thinking. All right. So the box plot, the way that it works is the one in the middle is the median. This is your Q1, this is your Q3. This will be your lowest value, your highest value, and then these right here would be those outliers. Anything that's identified as an outlier is a star. You got a real nice little tool to do this in your Alex.
So you did your lowest value and your highest value, then you have your outliers.
Yeah.
So would that be the,
These are the highest value that's not an outlier, lowest value that's not an outlier. And then any values in the data set that are considered an outlier are still there. They're just marked as a star. So, let's see how we do this. Remember, the median was 51, so it's just 1 over from 50 right there. And then, Q1 is 45, so right smack down in the middle between 45, 50. And then on this side, Q3 is 59, so almost 60. And you can see it pulled a little bit in that direction. It's not perfectly symmetric. And that's probably because of those outliers. Well, that one outlier. Now, you make your lines, the whisker part, they call it, and that's going to tie in the lowest and the highest value. So the highest value that was not an outlier, hold on a second.
They had it on the same side. Yes, look.
Oh, okay.
Right there.
So 77 is the first value that's less than the upper outlier value. Anything higher than 80 is going to be considered an outlier. So the highest one in there is 77, and they're going to put a little line right there. And then on this side, what was the lowest one that was higher than 24? I don't think there were any there on that side. The lowest one was 41. So that's what that is. And as I said is, well, they show it to you here on it's just evidently getting complicated, and I've never had to do that. And that's your outline right there, that's the 100. 77, 41, this was the median, Q1, Q3. And what that allows you to do is just see that there's a certain amount of pull on that side because of that outlier. Yeah, I just never have used it to do that. So, just in general, we're almost finished here. So if the median is pulled in that direction, there's a little bit of skewness on that side. That's what that means. That's skewed a little bit to the positive side or to the right. This one would be skewed to the left. So this is getting pulled, the medians get pulled in that direction. And there's two outliers they're showing us. We don't know what that data is, but they're showing us. And then there's one that's symmetric. More or less symmetric. Okay, so that's all I can think of for today.